we can in a minute go over to our more general discussion. But I just, yeah, Arkady.
No, no, thanks for the talk. I'm just trying to follow the point. In what sense there is a difference between classical and quantum gravity? Because if I'm considering this as kind of, like non-relativistic potential, for example, and it's quantum mechanics with non-relativistic potential, or I can say that it is linearized gravity. What I mean, so in this sense, not. I mean, the difference between classical and quantum in this sense, it seems. No, I mean. Kind of not clear to me. I mean, because if it's just quantum mechanics of these non-relativistic bodies, what is the difference?
I can only answer in an intuitive way, and I'll admit that this is not fully satisfying. But if I have an object that is either here or here, and then the question is, which direction does the gravitational force pull? If we were talking about the Coulomb potential, then the electric static force would have a 50% chance of pulling that way and a 50% chance of pulling the other way. And measuring the electrostatic force would collapse the superposition, and we would know where the object is. If gravity shares this feature, then I would call it quantum in this narrow sense. I'm not claiming I can detect gravitons or anything like that, right?
Yeah. I'm
just claiming that the experiment would show that gravity can be in such a superposition. But my understanding is that because the gravitational metric tensor in general relativity can't be in a superposition, what you do is you couple the Einstein equation to the expectation value of the energy momentum tensor. And so gravity would not pull left, would not pull right, it would pull to the middle. And so the experiment will do nothing more and nothing less to decide between these two cases.
Okay, I follow what you are saying, but I would say that to me, I would not see the difference between, say, Coulomb case and this one, because to the level that it is just like long-range potential, to me it sounds the same. Not the same, I mean, numerically, but I mean, in terms of interpretation. So that's why I'm asking, okay, I'm sorry that maybe it's not very much relevant, but it seems to me that on theoretical side, I do not see it's well formulated, kind of, because it seems to me that maybe it's not, at this level, maybe there is no choice.
I like your question very much, and unfortunately, I can't answer it, but I would love to hear what others are thinking.
Yeah.
I may answer.
Let me open up the floor to this question. I was wondering when it was going to come up. I'm glad it came up now. So, in fact, it seems to be the gravitational physicists have not come to a consensus on them. There's some gravitational theorists with very speculative ideas, there's no coherence at all or something. Then on the other end of the spectrum, there are people who say, well, you're not really measuring anything, it's just a longitudinal something or other. And so some theorists, including Ted Jacobson and Bob Weld, who are very widely respected, have thought about this carefully. Ted, are you on the call? Can you address the question of what does classical versus quantum gravity in such an experiment mean?
But if I may say something?
Yeah, please, go ahead.
I thought about this point a lot, and part of the reason I think with Andy we started this whole procedure. To answer Arkady's question, let's play a very simple game, Arkady. I give you a coin, and let's imagine that coin is quantum. Okay, and I keep a coin. I'm sitting in Groningen, and I imagine that my coin is quantum. I request you to toss the coin 1 billion times, and I do the same. I toss the coin 1 billion times. And let's say we don't have any other interaction. There's just a purely, let's say, classical interaction, classical scattering, like playing football, nothing more than that. You would, if you would do this experiment, you will get 50-50, 50% up, 50% down. And I would also get 50% up, and I will get 50% down. However, if there is an interaction between you and me, if I set up, which is quantum in nature, then this will not be 50-50. It will be maybe 51, 49, or whatever. So what it tells you that I'm able to influence your experiment and you can influence my experiment. And this can happen provided you have set up some kind of quantum communication between you and me. And think of this exactly in this way. If gravity is purely classical, then it will never entangle the two systems. And if the gravity is quantum, although it's a Coulomb potential, although it's exactly like the same potential what Newton told us 400 years ago, but the fact that if the graviton is quantum, the off-shell interaction can entangle the two masses. So that's the subtle difference which perhaps...
But what about, say, electromagnetic force? Let's say that it is charged particle, I mean, whatever. Well, I mean, then you think it's also would be a way to check it this way?
Exactly. Exactly. You can exactly.
Right, but in case of electromagnetic radiation, you have no doubt that it is kind of classical and quantum at the same time. It is in this sense there is interaction, right? Okay, and I would say that at the T level, to me, quantum it is where loops are important perturbatively. Where loops are not contributing, then classical field theory or quantum. I mean, okay, it's so I am trying to make a point about, say, kind of loop corrections versus T level. T level is equivalent to classical theory. So, and what you are saying, it looks like a T level. That's why I do not see, kind of differentiation between classical and quantum at this level.
Yeah, I mean, from formal perspective, I agree that there is no loop diagram, because anything with loop will be very, very suppressed. You will never ever be able to detect it. But the fact that this entanglement feature is there in any scattering process, you can take even molar scattering, Bhabha scattering. These are all T-level processes.
Okay, but then at this level it is and in this way there is no difference between electromagnetic long range and gravitational long range. So it's classical and quantum at the same time. No, I mean kind of a small amplitude of fluctuation you could relate it to. Okay, but
so let me ask, what would you consider molar scattering or Bhabha scattering? Would you consider them a classical scattering or a quantum scattering?
At T level, I do not see the difference.
No, the answer is the same, but the process is, of course, there is an off-shell. You buy the concept.
The notion of shell is unphysical. It's just about theoretical way how we're calculating this.
Absolutely. But the subtle difference is that in the classical, if it were classical scattering, you would never see this entanglement. So what it means is that there is no spin-spin correlation. There will be no helicity correlation.
No. At the T level, you can have scattering accounting for all correlations. And I would hesitate how to call it classical or quantum. I mean, in this sense, it's quantum. At the T level, right? That is not exactly classical, but this would be not an interpretation. It would be like numerical difference.
Let me say this. Let me say this a little bit differently.
Yeah.
If you do an experiment where gravity should entangle, but yet no matter how hard you try, you get no entanglement, this is an indictment of a linearized theory of quantum gravity.
Yeah, okay.
That's what we really mean.
Yeah.
It's not saying, it's saying that something's wrong because it's not entangling and it should. That's what we're talking about.
Yeah, I think that's exactly right. Experimenters on the call, when the theorists are arguing this vociferously, all the more reason to do an experiment, right? Let's see, Lance, what do you have to say?
My definition of quantum gravity is if you don't have to quantize the gravitational field, it's not quantum gravity. That's my definition. It's clear people have different definitions, but that's my definition. And also, I think the statement about loops versus trees is a little bit confusing because, I mean, recently people have been calculating scattering amplitudes in classical gravity by using loop techniques, and there's nothing wrong with it. If you exchange multiple classical effects of a field, it looks like a loop diagram, but it can still be classical.
No, that's true. But look, quantizing in linearized case, quantizing it's of course is there, right? So you can say that you can quantize small fluctuation. I mean, there and in this way. But okay, but this would be there is no then boundary between, in this sense, between classical field theory and quantizing of linearized approximation. I mean, there is no, no. I mean, of course, I agree that but maybe I'm getting it wrong. My impression is that when people are talking about classical gravity, they are arguing that there is no need to quantize this small fluctuation, right? And it is to me sounds strange.
But I also thought that the quantum effects of gravity have already been seen in atom interferometry or in neutron interferometry before that. The phase accumulation that goes from taking different paths is produced by an external gravitational field, and that it's already been seen in those fringes.
But Lance, that doesn't show the quantum superposition principle for the gravitational field itself. That's the crucial thing.
Okay.
No, that's the effect of a classical background field on the Schrödinger cat state of some other system, an atomic system. It doesn't show the superposition field for the gravitational fields. The crucial issue is, does the macroscopic gravitational field satisfy a superposition principle or not?
Does that mean that it's quantized, John?
It's a crucial stepping stone to you having to have it. It's necessary.
Okay, but it's not sufficient to show that you needed a full quantum description.
No, but I certainly say it's a necessary part of it.
Okay.
Yeah, there are several stepping stones, and they're all important experimentally. They're all important experimental benchmarks, I think.
I think one example I can give, because I've been thinking about these problems a long time. So suppose if experimentalists can ever create very thin, long strings, and the beautiful aspect about strings in 3+1 dimension is that it doesn't gravitate. So, I mean, at the free level. So exactly to answer Arkadi's point. So suppose if I can construct superposition of two strings, then there will be a one loop computation, precisely which Arkady would love to see this kind of experiment one day. But the problem is that it's suppressed by G square. And the effect becomes so tiny that maybe even with 50 years technology, it would be very, very hard to do. But maybe, let's say, 100 years, if one can do that, that will be really, really wonderful experiment. Because you are really seeing one loop effect in the superposition as well as in entanglement.
Yeah, good. Okay, Dave. Dave, you're still muted. Are you there?
You're muted.
Sorry about that. Can you hear me now?
Yeah.
Yeah, so thanks for both of those talks this morning. I've actually got a question for Peter about this idea of using asteroids for detecting low-frequency gravitational waves. I've been thinking about the role of clocks in those measurements. So if I understand properly, the clocks are located on these asteroids, and they're sending out very regularly timed pulses, and you're measuring the arrival time of those pulses relative to the local clock. And what that gives you is a distance measurement between the asteroids. So if I understand that correctly, it seems like if you instead have a third asteroid, you have some source of pulses there, and you send it out simultaneously to the two other sources. You have a retroreflector, and then you measure the arrival time coming back. It's much more similar to the LISA concept, and it would reduce the requirements on the atomic clock almost to trivial requirements at that point.
Yeah, definitely, exactly. It's the usual sort of trade-off that we have even in the millihertz band, sort of just like the nice atomic clock paper was pointing out, okay, the atomic clocks give a different way to pick up, let's say, that same sensitivity curve that LISA picks up. With the atomic clocks, indeed, you would, in principle, only need a single baseline, whereas you need two baselines or a triangle. if you're not using an atomic clock. Exactly, that's right. But exactly as you say, you can either use the multiple baselines like LIGO and Lisa do, or you can just use really good clocks and then a single baseline. That's right, and you definitely have that choice here too. So in principle, yes, and that's also definitely like an interesting mission architecture to keep in mind. It does worry me more. I guess I suppose it's also partly a question to you how hard you think it will ultimately be to make a space qualified clock at this 10 to the minus 18 level. The reason I say that is running this triangle with uncontrolled proof. So Lisa, of course, has very carefully chosen the orbits of their satellites, right? So the relative motion between the proof masses is minimized, whereas you can't do that with asteroids. You have this huge relative motion. And to me, that makes it sound like, so they have, tight specs on the relative, differential arm length change between their different arms, right? You can't do any of that. I mean, the arm length, these things got some eccentricity. The arm length will be changing by, 0.1 AU or something.
Mm-hmm.
So that's what led me let us to begin by thinking about atomic clocks. But yeah, in principle, that's not a, let's say, this is where we started because we were mainly focusing on how good the proof mass is. So I think, yeah, considering all options is still very interesting for sure.
Yeah, I don't know exactly where the best trade-off lies. I mean, I think if you can avoid having to get a 10 to the minus 19 level clock in space, then it's worth thinking about. And, delivering retroreflectors to a bunch of asteroids and using numbers in that way to get rid of some of these systematic effects like what you're talking about seems like an attractive option to me. So it's an interesting thing to think about for sure.
Yeah, no, definitely. Absolutely. That's a very interesting comment for sure. Yeah, you need the link on every asteroid. So you need the transmitter, you need the receiver and transmitter on every asteroid, on or near every asteroid. But yeah, absolutely, it's possible that ends up as being the way to go.
Oh, why could you not just do retroreflectors on every asteroid?
Well, okay, so it depends what baseline you're going for, but we think we really do want a pretty long baseline, and then you really need the power source. You lose too much. Your shot noise will become very small if you just have a retroreflector. Same way Lisa does, even with a much smaller baseline. I didn't really go over it at all, but the link noise curves I showed just assumed that's the link noise for one way, not for across and reflecting back. That would be much, much worse.
Okay.
But that may be fine. I mean, however, what you're saying, I think is still very interesting. I mean, like I said, that's the other sort of mission architecture and very much worth keeping in mind. There's no real reason you can't have a satellite just hovering near or on an asteroid.
Right.
Mm-hmm. Oh, thanks.
Yeah. Anupam had his hand up for several minutes now.
No. So I think the dream thing would be to send these clocks to the Kuiper belt. If NASA is willing to do that, that would be fantastic. Because of course, this is just my dream that if you're sweeping past through the empty space, and that might be a way to even see if there is a neighboring black hole sitting there. And which our observers will perhaps never be able to detect it, but such a clock would be able to detect it. Actually, would see if there is any small, gradient, gravity gradient noise if it picks up. Mm-hmm. So I think this program of clock is fantastic if we can build something like this.
Yeah, absolutely. And in fact, you also win for gravitational waves and everything by going farther out in the solar system. Would be very interesting. I agree. I don't know how to cost that, but I'm not a satellite engineer, obviously. But yeah, for sure. Yeah.
Pioneer 10 picked up anomalous accelerations for a while. But that
Yeah.
was like full DC, so I don't think you have to worry about that if you're not going to go into the full DC mode. But yeah, they had to track all the outer bodies, but there are a lot less outer bodies than there are in the asteroid belt. So
right,
that helps a lot.
Yeah, we think going out really helps with that asteroid gravity gradient noise, for example, I was talking about.
Yeah.
Yeah, you know, and yes, not being at DC is crucial. Yeah.
Any other questions for our two morning speakers in the latest morning session? Any other topics to raise? I just exchanged email with Ted. He said he had to leave for a committee meeting. You know, we're all professors and scientists. We have to go to committee meetings, and he left at exactly the wrong moment. I'll certainly twist his arm to make some comments tomorrow, both on his own behalf, and he's also read Bob Wall's paper carefully, which speak to this classical versus quantum debate.
Can I make a comment just on this side
Please.
topic for a second?
Yes.
I think Lance, I'm not sure, Lance, you asked a question to Peter about nanograv and that Gaia line. My understanding is that people have claimed that Gaia, once it runs long enough, and that's the crucial time, can be much more sensitive in that frequency range to things like cosmic strings or some background stochastic thing than the nanograv. But I think it requires a minimum running time of something like 5 to 10 years.
Right, that makes sense because it's extremely low frequencies. Yeah. But have they presented any results on shorter frequencies yet? It sounded like that was a proposed sensitivity.
I don't know. It's a very good question. But as you know, there's a huge amount of data coming out of Gaia. Lots of different other groups also processing it, using it.
And maybe it's all public. You can do it with the public data, or you need to have the collaboration.
That would be great.
I don't know.
Okay, anything more?
So maybe this is a big question to bring up this late in the session, but I was really curious, Peter, about the ideas using trapped ions to detect milli charged particles, I think it was. I wonder, can you give me a high-level overview of that?
Yeah, actually, I'm happy to. Yeah, I can give you the 1 minute version maybe. And then also I'm happy to follow up with you and or anyone else. I was actually ashamed that I went too slow. I wanted to talk about that too. I'm excited about it. The basic idea is the following, that, so we were talking about milli-charged particles, and what I can show you in more detail, but you just have to believe me for right now, is that, there's been a lot of interest in milli-charged particles recently, and a lot of the interesting parameter space where I think actually Lance or someone was explaining this earlier. If you had a loop factor that was suppressing your kinetic mixing, things like that. Let's say I've got charges, 10 to the minus 1, 10 to the minus 2, down to maybe 10 to the minus 4 or 5. Those are actually, although much smaller than the charge of an electron, large enough that they do a lot of scattering in the Earth. So if they're out there, if they exist, when they hit the Earth, they don't really make it to deep underground detectors, making it very hard to look for them in any of our traditional dark matter experiments. So I'm glossing over a lot of subtleties here, but that's the basic idea. And then in fact, actually, in some sense, one really big problem is that they thermalize in the Earth. So they become 300 Kelvin, which is about 30 milli-eV in kinetic energy, which is way below the threshold of any of the dark matter detectors we build, as you may know. Right, so particle physics, we usually, in particle physics, right, we're making a low threshold detector. That might mean maybe we get all the way down to electron volt threshold energy deposition for a dark matter detector. And that would be great. That lets you look for light dark matter. But not 30 milli-eV, which is what you need to see something thermalized to room temperature, which is an interesting scale anyway, and millicharges provide an example. What we got excited about, though, is that you do have a ton of these things. I mean, they get stuck in the Earth. There's a lot of them around. If there's even a few out there, they pile up in here because they're thermalizing. They're getting stuck. So it's a funny population. You're looking for a huge number of pretty low energy things. We sort of, in short story, is it looks like ion traps are really ideal for this. They're really optimal, right? They have, you can see really low energy kicks to them. They're in that sense, they're a fantastic particle physics detector with a really low threshold. They don't have a lot of target mass, right? Compared to tons of xenon or something. You have a few ions in your trap, but that's okay. These are particles with high charges, so very high scattering cross sections. So, and large number density. So actually the ion trap may be an awesome, really optimal dark energy detector for this kind of particle with low energy deposition, but a very high cross section. So that was maybe the 1 minute summary. But I actually would love to talk to anybody who's interested in ions or anything more. So.
Yeah, that sounds like something that'd be really interesting to look into in a little bit more depth. There are several experiments in our group that, could do measurements in that direction, I feel like. So.
Perfect. That'd be great. Well, yeah, maybe I'll follow up with you and anyone else who's interested. Yeah, just ping me, send me an email or something.
Yeah. Flaminia has her hand up. Please go ahead.
Yeah, so thanks a lot. So I just wanted to give a comment on this result by Bob Wall that was mentioned, because I've actually worked on that as well. I'm an author of that paper also. So maybe I can. No, don't worry. But yeah, maybe I can tell you briefly what the content of that paper is.
Please.
So basically, it's a thought experiment where you have, in quantum information language, you have two parties, Alice and Bob, and each of them has a particle. So here you have a particle Alice that an observer Alice that has a massive particle that produces a gravitational field. So it's the source of a gravitational field. And the setup that you use here is linearized gravity. So it's what has been discussed in this discussion session before. And initially Bob holds his particle in a trap. So it doesn't feel the gravitational interaction. And you open the superposition in Alice long before the experiment starts, so that basically the Newtonian field is not an approximation. So it is exact to treat the gravitational interaction just with the Newtonian field. And then at some point, Bob can decide whether to release his trap or not. And if Bob releases the trap, then the particle of Alice and the particle of Bob and the gravitational field become entangled. Whether if Bob does not release the trap, the state remains separable. So now imagine that you want to describe everything, but just with classical gravity. So, but you still keep the fact that you have a Newtonian interaction. So basically, so the key point, the crucial point of the discussion is that unless you consider vacuum fluctuations of the gravitational field and the emission of gravitational radiation in a superposition, and remember that using the Newtonian field was not an approximation in this result, then you end up with faster than light signaling. So basically, Alice can know whether Bob released the trap or not before a light crossing time. So So the fact is that you only use the Newtonian field here, and you didn't need any retarded potential or anything because the situation was static. Like Alice doesn't move the mass before, so it's really no approximation. So it seems that you're forced to introduce some quantum features of the gravitational field, and you cannot simply explain. So either you have to give up no faster than light signaling principle, or you need to introduce some quantum features of the gravitational field in the description of this thought experiment. So the thing is that, of course, the crucial point here is the locality. So you need to assume that gravity mediates the entanglement. But once you do that, then it is not a problem to treat it with the Newtonian field, and you are forced to introduce these quantum features of gravity. So maybe, I don't know, this is just a small contribution to the discussion.
That clarifies things greatly for me anyway. Thank you very much.
Thank you.
We're running way late, but the discussion has been worth it. Well, people can go to lunch anytime they want to. Let's keep talking here a little bit. Anupam.
Thanks, Ramena. It's good that you explained it. But one thing which I was a bit cautious about as you were speaking, that suppose even if you take a matter wave interferometer, it doesn't release that many gravitons. Even though it's a trap, it's actually, you can think about it as a kind of like a, two black holes oscillating around each other. But the number of gravitons, the on-shell gravitons it emits is so tiny that's almost negligible actually. So yes. It's not the on-shell aspects which is important. It's just the off-shell fluctuation that's important here actually.
Well, but in any case, even if the number of gravitons is very small, then you will always find that there is a threshold, so which depends on the distance and on the energies. So it's really a delicate balance between all the different physical quantities that are at stake here, which makes it possible to have faster than light signaling. And of course, if you have less graviton emission, then you will also have less gravitational interaction. And it all depends on the distance between Alice and Bob and how big your superposition is and how massive your particle is. So there are different physical quantities that combine perfectly, so that basically you have no paradox if you have no faster than light signaling if you take into account these two elements, like vacuum fluctuations and emission of gravitational radiation. And yeah.
Igor, did you want to follow this up?
Yes, sure, if I may. Yes, so I was following the discussion passively, was putting my kids to bed. Finally, I managed. So I just wanted to mention one, I think, issue which hasn't been said, but I think it can greatly clarify the issue between classical and quantum here. Namely, it all revolves around the notion that we work in the Newtonian limit. So in the Newtonian limit, we just have the gravitational potential. We have a perfect theory without any quantization, just a potential, and it entangles our systems. So from that perspective, it's purely classical. I think the statement to say that such a source test masses can probe quantum gravity relies on one additional assumption. And I don't think this has been stated here explicitly, but this is always implicit in all these formulations. Namely, the assumption is that gravity is described as a local field theory. And this does not work for a classical local field theory if it has to entangle system. But so then if it's a local field theory, it has to be quantized in order to entangle these systems. So there is a classical description which is perfectly valid, which is just Newtonian instantaneous action at a distance. That would be fine, that would be sufficient. But if you assume it has to be a local field theory, that has to be quantized. So I think it's in this sense that these experiments can probe some type of quantum nature of gravity under this additional assumption.
Yeah. Actually, can I say something?
Yeah, please.
I mean, yes, I agree with that point, actually. I mean, it's, at least I think both papers by Newpem, but also by, Vlatko Vedrol and others and Mileto who worked on this, say, explicitly, you precisely can't have a non-local interaction, right, that's going on in some sense. Otherwise, the theorems for a classical channel can't entangle, two quantum systems actually breaks down. But can I say something? I think it's a little bit confusing. I think this is the thing that worried Arkady, to always phrase things in terms of virtual gravitons. We know we can always formulate all field theory calculations where you never use the phrase virtual particles, right? That's not the way. I agree. It's a sort of gauge and description dependent way. You can always really do things with everything on shell. And so I think it's useful sometimes to rephrase those statements in what was going on in terms of on-shell gravitons.
But Igor, I'm trying to say that when you're quantizing, like a local field theory, kind of linearized gravity, it still has instantaneous interaction, even with quantization.
Yes.
Right? So then the question is whether experiment is sensitive to, something which beyond instantaneous interaction. If it's not sensitive, then it doesn't matter, right? Because it is the same instantaneous interaction as a Newtonian limit. And then I need to find this experimental signature of non-locality, the one which John mentioned, right? That it should be something which is beyond, this instantaneous interaction, right? To signal, difference between, say, I don't know, electromagnetic case and this one, right? And I do not see this was pronounced because entanglement by itself would be, like in, say, like you said, it would be like a normal instantaneous interaction, even with quantization. So we need to have additional signature.
Well, I think it's one of the issues that are really pushing on, but this is the second or third stage experiments. You'd want to do it such you can actually see the causal nature of the entanglement building up, right? I mean, that's the crucial thing, but that is super hard to do, right? Because you need very short. Yeah.
John, it's very interesting. Very interesting. I love it. What both of you are raising the issue is very interesting. In principle, one can do it also. So imagine you can test exactly the locality of the quantum field theory. Suppose you create the say two Stern-Gerlach apparatus. You keep one inside the light cone, but you because right now the clocks are very good. They can reach up to the precision of 1 part in 10⁻²18. So if you drop the other one inside the light cone, within this precision of 10⁻⁻18 second, you can even test the light cone structure of the essential field theory. And that's something beautiful thing which, one can, in principle, one can do it. Of course, in reality, it would be very, very hard.
But yes, I didn't think I agreed in principle, but I think in practice, you can't do the gravitational entanglement of things in that causal way. You would want to do that in the end. Right?
Yes, you would want to do that.
Yeah. No, but I mean, but it is suppressed if you are with non-relativistic system. Then all this kind of non-locality effect would be suppressed by by this non-relativistic parameter, right? So it would be so you need something where so in this way you are sensitive to finite value of velocity of light, right? You should be sensitive to this.
Mm-hmm.
So one
yeah, I think we better bring this to a close in just a minute or two. Animesh, you have your hand up. Please go ahead and please keep it quick.
Yeah, thanks. I think to crystallize what's sort of going on, what you really need is a loophole-free Bell test of entanglement generated by gravity, right? That is really what we are talking about here. And that, I think, would be the unambiguous signature of quantum effects of gravity. Now,
interesting idea.
That has not even been done with the nuclear forces, because you would have to do your experiment on a time scale of, I don't know, 10 to the minus such a large number. So, I mean, yeah, it may happen someday, but I think that would be the ultimate loophole-free, unambiguous test of quantum aspect of gravity.
But I disagree with that, if I may say. There's a confusion, namely, if gravity induces entanglement between other systems, whether you have a Bell test of these other systems or not, will not resolve the issue that's raised by Arkady. Of course, the ultimate test is, Bell test of gravitational degrees of freedom themselves. That's, of course, a different story, but that nobody has a clue about the experiment. So I don't think what you're saying would address the issue raised by Arkady. I think the Arkady's issue just goes down to the fact that if we know how to get the Newtonian limit of any field theory, and in the Newtonian limit, we have a classical interpretation, and that just is a potential in the Schrödinger equation, and we cannot tell much about where these hidden degrees of freedom come from. So I do think there's this additional assumption one needs to assume that there's some degrees of freedom which are themselves some kind of local degrees of freedom that induce this interaction.
No, I think so I was probably sloppy in stating that. So I think the degrees of freedom in which you violate your Bell inequalities, is an important consideration. So if you, for instance, so if you sort of did the kind of experiment that people have talked about, which is entangling sort of superpositions of masses and doing spin readouts, I think if you did a Bell violation of the spin degrees of freedom, that would probably not constitute a proof for the Bell violation of gravity, I think. That's what you're saying, right, Igor?
Right. I think it would be the same objections Arkady is raising.
No, I agree with that, I was sloppy in my statement, So you would have to do the Bell violation on some sort of center of mass position degree of freedom of the object. I don't even know what that would be, actually.
But Animesh, this is what the whole proposal is. This is what the spin entanglement witness for quantum gravity is. It is equivalent to a Bell's inequality test.
No, it's not a Bell test, right? Because to do a Bell test, you have to be sort of separated by a distance within which the light cannot communicate the information, right? That is precisely the reason why sort of the loophole-free bell tests are done with these sort of huge experiments sort of kilometers apart, right?
Let's see, I'm going to use my chair's prerogative to cut this off. We'll have plenty of time to talk tomorrow. I'll give the floor to Flaminia for one last comment.
Thanks. No, I just wanted to actually reinforce Igor's point and to say that I also think that the real challenge is to show that the masses locally interact with the gravitational field, which would amount to saying that the gravitational field is a mediator. And without doing that, I think one cannot conclude the main point of what we're saying here, which is that gravity is the mediator of entanglement. And so what to distinguish the nature of the gravitational field. So that's one of the main issues in this, at least experimental, and I don't know how that would be achieved.
Yeah, good. Well, I'm going to applaud all four of the speakers today, Holger, Peter, Jason, and Jamie, and all the discussants too. This has been a great discussion. We'll have plenty of more time tomorrow. There will be more talks tomorrow on these very subjects. So thanks for all for coming. See you at 8 a.m. California tomorrow.